Before getting into the details, let me talk about fixed points. So suppose we have a domain with the least and the greatest element, bottom and top respectively. All elements in some part of the domain will have the following condition, which means that if you apply this function f sharp to an element, this x sharp, you will get a larger or equal element. Okay, all such elements are called prefix points of f. Obviously, the bottom is a prefix point. Okay, so there exists an increasing chain like this. Okay, whenever you apply this f sharp to an element in prefix point, okay, then you will get a larger element. The dual set also exists. That means that if you apply this function f to an element x sharp, okay, you will get a smaller or equal element. Okay, all such elements are called post-fixed points of f. Obviously, the top element is a post-fixed point of f. Okay, so there can exist a decreasing chain like this. So whenever you apply this function to an element which is a post-fixed point, the outcome will be smaller than the income. Okay. And then what about the intersection in between? An element that exists in the intersection is actually called fixed point. Okay. There can be many fixed points, as you can guess. So among them, the largest one is called greatest fixed point, and the smallest one is called the least fixed point, which is the ideal analysis result. Okay, then the goal of static analysis is to compute an overall approximation of the least upper bound of the infinite increasing chain from the bottom in finite time. Okay, so to do this, we will use a binary operator called widening. This widening operator will make a big jump like this and ultimately make a finite chain. Okay, after one iteration with widening, we get here. Okay, and after another iteration, we get here. And after a finite number of iteration, we will be over the ideal result like this. Okay, which is a sound approximation of the ideal result. But sometimes the analysis result by widening becomes too imprecise because of too aggressive over approximation. So for this case, we use an operator called narrowing that refines the analysis result from widening. That starts from the result of widening, and application of narrowing operator will result in a refined result. Okay, and one more application will refine further, and we keep doing this until reaching the final element of this decreasing chain. This step can be done also within finite time. Okay, then finally this is the final analysis result. First, let's talk about what the finite increasing chain by widening, such that each last element is larger than or equal to the ideal result. The finite chain by widening is defined as follows. It starts from the bottom, okay? And if it reaches a post-fixed point, then what does that mean? The application results in a smaller or the same element. Okay, then it stops there. Otherwise, we apply widening to the input and the output of f. That will be the next element on the chain. Okay, here notice that widening operators are in general not commutative. So you should be careful of the order of argument here. Okay. Let's take a look at how widening works. Suppose there exists the original chain by the semantic function f sharp. Okay, this will be infinitely long. The new chain with widening defined as follows. The first element will be the bottom. Okay, and the next element is defined as a widening result of y0 and f of y0. And the next element is also defined in the same way. And after a finite number of iterations, it will reach a post-fixed point. Okay, and then it will stop there. That is how widening works. Okay. Then the next question is that how to design a widening operator for my analysis correctly. Okay, what conditions are required to ensure the correctness of widening? That is our next question. And then, what are the requirements for widening operators? There are two conditions that a widening operator must satisfy. The first one is that the widening result of two elements should be larger than or equal to the input element. Okay. Intuitively, that means that widening is an over approximation of join. And the next condition is that for all increasing chain hold X, the following increasing chain defined using widening should be finite. That is the next condition. Okay. If these two conditions are true, then the followings are true. Okay. The chain Y with widening is finite and it subsumes the ideal analysis result. Here is the proof. If a widening operator satisfies the conditions we discussed before, then the chain by widening, okay, this chain will eventually stabilize, which means that it will be finite. And the last element will be larger than or equal to the ideal result. Okay, the proof actually consists of two parts. First one is that the chain is finite and the last element of the chain is larger than the ideal one. Okay, the proof is not going to be difficult. It can be done by using the widening conditions and monotonicity of the semantic function. I recommend you read this proof and do the proof by yourself as a practice. Next, let's talk about the finite decreasing chain by narrowing, such that each last element is still larger than or equal to the ideal analysis result. Okay. The finite decreasing chain by narrowing is defined as follows. Okay, it starts from the widening result. And then we apply narrowing to the input and output of f. Okay, that will be the next element of the chain. This chain will be finite. Okay, then let's take a look at how narrowing works. Suppose there exists a chain of the semantic function f sharp starting from the widening result here. Okay, this chain will be infinitely long. The new chain with widening is defined as follows. The first element, okay, is actually the widening result. Okay, and then the next element is defined as a narrowing of C0 and f of C0. And the next element is also defined in the same way. And after a finite number of iteration, it will stabilize. And then it will just stop there. That is how narrowing works here. Okay. Then the same question is here. How to design a correct narrowing operator for my analysis? what conditions are required to ensure the correctness of narrowing operator. Here are also some requirements for narrowing operators. There are two conditions that a narrowing operator must satisfy. The first is that the narrowing result of two elements should be in between the two input elements like this. Okay. Intuitively, this follows that the narrowing result is always in between the widening result and the ideal result. Okay. And the next condition is that the chain, okay, for all decreasing chain X, the following decreasing chain Yi defined by narrowing should be finite, okay, which is similar to the widening case. Then the followings are true, okay. The decreasing chain C by narrowing operator will be finite and it finally subsumes the ideal result. Here is the proof. It can be done in a similar way to the widening case. So the first sub-goal is to show that the decreasing chain is finite. Okay, that can be proven by induction and the conditions on narrowing operator. Okay, and the second sub-goal is to show that the narrowing result subsumes the ideal result. This can be also done by induction. Okay, I recommend you prove this by yourself as a practice. Okay, in summary, we have covered the abstract interpretation framework. Abstract interpretation is a framework for designing correct static analysis. If your design satisfies these two requirements, first one is Galois connection, and the second one is the soundness of semantic function, then the soundness of your analysis is guaranteed by the fixed point transfer theorem. Okay, and additionally, to guarantee termination, widening operator is introduced that computes an over approximation of the ideal result. And to refine the widening result, narrowing operator is introduced that define the widening result. That's the abstract interpretation framework.